Good evening. We'll go ahead and get started now. It's 6:15. I want to welcome you all to Jaywalking, the intersection of technology and sound, a bird's eye view of how programming can be used in sound and music. But first, a disclaimer. These are opinions, observations, and brain droppings of one person. This talk is only intended to show you one person's ideas and to inspire you to be excited, investigate into, or find them used by creating with technology in the world around us. About this talk. The intent of this talk is to give you a 1,000-foot view of some of the things possible when programming with technology, music, sound, and for creation and performance and production. This is an overview of some of the fun libraries I've come across and some of the projects I've created that have failed in use or are still being put together. Okay, so about you guys. You're all artists or creators or programmers in some type. Any musicians? By a round of applause, any musicians? Okay, wow. Hey, we're musicians, we like applause. Producers, engineers of the audio flavor? Okay, so we've got a programming crowd this evening. Outstanding. So how many folks are full-time programmers? Outstanding, cool. So, I bet you're wondering who's the pushy guy asking all the questions. Well, my name's Tony Sprayberry, and I work here at TelTech. I work on the spoof card team, and my alter ego is Muse Talks. There is a SoundCloud and a Facebook that I don't check. Feel free to look at the tracks I posted a few years ago. Like I mentioned, I'm a full-time software developer here at TelTech. I work on spoof card, which is a fun way to prank your friends by changing your number. I'm an all-around geek. I like science. I like the way things work. I'm an amateur radio operator, which is a lot of fun, and we'll touch on that very briefly later. But on top of that, I'm a musician, sound designer, composer, mixer, and audio engineer. I did that professionally for about 6 years in the post-production world, and I did live before that, and I've been playing music since about 20-some years now. Why are we here? Because music and technology are awesome, and we're gonna jump to some quick basic concepts and see how we can look at these things. So what is sound? Sound is a transmission of vibrations, but specifically, vibrations transmitted through an elastic solid, a liquid, or a gas with frequencies in the approximate range of 20 Hertz to 20,000 Hertz, capable of being detected by human organs of hearing, i.e. your ears and skull help with that. So there are sounds that exist below and above those frequency ranges. I mentioned amateur radio. In the amateur radio service, sometimes sub-audible tones are used to open up gateways on repeaters and stuff like that. This way it doesn't actually interfere with the transmission of the voice, but sub-audibly, the radio on the other end hears this 10K or 10 Hertz tone underneath your voice and opens up so you can speak to people on that repeater. So there are tons and tons of different ways sounds are used for signaling and processing like that. So how can we represent sound? Visually, of course. A spectrograph is one way, and that's a picture of a spectrograph. Specifically, that is the RX3 isotope spectral analyzer. It's a very nice plug-in by Isotope. It's kind of expensive, but it's really handy when you start getting into sound removal and stuff like that, when you start doing post and things like that. So quick explanation of what you're seeing, those pretty colors. Up and down on that graph is frequency, and right to left is time. The color intensity shows amplitude of a specific frequency over time. So you can see those vertical lines are frequency instances over that time frame. A human voice operates in about the 300 to 3,000 Hertz range. That's the fundamental frequency of the human voice, from baritone men to high-pitched women. So on top of that, you have harmonic frequencies, and what you're seeing there is that stacked effect. The lower frequency is the primary or fundamental frequency of a voice, and those other ones are the harmonics that give voice its intonation and specific tone to each person. Other ways we can look at sound is a waveform. Now this is a little different. A waveform is up and down as amplitude, right to left being time. What shows frequency is in a waveform is frequency, how frequent a waveform happens over time. So a closer waveform would obviously be a higher frequency, longer waveforms would be lower frequencies. Another way to say it is an audio wave is a vibration of air molecules, which is how sound travels. A waveform describes a wave by graphing how an air molecule is displaced over time. So that's quite literally, those vertical waves are how you can imagine an air molecule in the air vibrating with your voice or some sound going through it. So those are the basics of sound. What's music? Music is the art of arranging sounds in time as to produce a continuous and unified and evocative composition as through melody, harmony, rhythm, and timbre. And basically, like I just said, it's a group of sounds. So how can we represent music visually? We can use sheet music and chord charts. That is the sheet music, and separately the chord chart for Starbark Affair, an old classic song redone by Simon and Garfunkel, most popularly. Additionally, on top of that, for us lazy guitar players and stringed instruments players, there's tablature. Tablature kind of looks like that, and each line represents a string on an instrument, and the numbers correspond to the fret on the instrument or the position. Right to left is obviously time. So with those few basics in mind, let's look at some utility functions of programming or SOX, PyDub, and IPD. Oh my! One of the more common things you're going to find, and this is case in point in SpoofCard, we're working on a feature right now, actually a test, to test our features. So we use voice changers and background noises in our spoofing app. And what we want to do is make sure we're not having any server problems, and we want to test them periodically throughout the day by placing a fake call and analyzing the audio on the other side of that call that we record. So what we're going to do with that is use that to make sure pitch changers or voice changers are working. So we're going to talk very briefly about frequency detection, aka pitch tracking and frequency estimation. There's a bunch of different ways of doing that, different algorithms. There's the FFT music and a couple other ones I can't particularly pronounce. They're all different ways of doing it, but basically they are ways of counting your waveforms over time and determining a frequency in a given period of time. So I mentioned the practical application of testing our voice changers. And back a long time ago, before things like SOX, you used to have to import SciPy and do a bunch of other things and take your sound waveform, SpoofCard's down, take your sound waveform and count the frequency peaks, and you can figure out what the frequency is on average for that specific file or that specific segment of time of sound. But with SOX, all of that now becomes 3 lines. SOX is an incredibly wonderful library. I can't wait for a Go implementation of it that isn't 5 years old. But it's definitely worth taking a look at if you find yourself in a situation where you need to work with sound and sound files. SOX is a pretty great library. Additionally, for background noises, when we go to check those, we're going to obviously see if this recording is silent or not, so we'll do amplitude estimation, and we'll see if it's silent. Once again, SOX to the rescue, taking that information and making it very, very easy to ascertain just by getting the maximum amplitude or the mean amplitude of any particular file. So more quick practical applications. Other things you can do are change the audio channels, take a stereo file and make it mono, vice versa. You can separate files or channels. You can also do multi-channel processing. 5.1, quadraphonic sound, which came and went years and years and years ago, but that concept is still very much used in sound, especially some of the more experimental music. You can still find quadraphonic recordings and get 3D picture of your sound as, you know, violins swirl around your head. It's pretty cool. And that's just one of the ways of taking an audio file with PyDub this time. And you can take an audio file and you set its sound channels to 1, and it will compress the 2 stereo channels into 1, and then you can re-output it in the format of your choice. Additionally, you can use it for format conversions, MP3 to WAV, and OGG, and AAF. Just another quick example, SOX makes this stuff one-line things. Years ago, you'd use, or before the popularization of the SOX Python library, you would find yourself having to use the Python wave library, decode the wave file, grab its channels, put it back together, and re-export it. This takes all that and extracts it away to that one liner. And of course, metadata. ID3 tags. When you have MP3s and you're doing large uploads, like I mentioned, I worked in the post-production world, and I found myself having to change ID3 meta tag data in large frequency, so I would create a text file of the information, comma separated, and then use that in a loop to go ahead and change ID3 tags in mass. Once again, another super simple thing with socks. So if you want to learn more about this type of stuff, you can go ahead and check out the Python wiki. There is an audio and Python and music page. There's tons and tons of awesome links, references to all of those things. Also check out ID3-Pi, was one of the earlier libraries, or other libraries, I should say, that works in a similar way to ID3. Now, music utility. I just want to kind of run over some ideas and concepts that I've kind of worked with and that are working on right now, in that music is math. If you take chords and scales, they're intervals, they're musical numeric separations between tones. So you can use that with Python or other languages to create compositions, create scales, look up scales, things like that. And I'm in the midst of creating this. I'm sorry, it's really hard to see. I should have made or actually just, okay, sorry about that. Anyway, that's a series of functions that will then take MIDI notes, or I'm sorry, an empty Python dictionary, and turn that into MIDI notes 0 to 127 and the corresponding actual musical tone and octave. So what that will actually give us when printed out is that dict, as I mentioned, starting at note C on the -2 octave and then stepping its way all the way up to note 126 and F sharp in the 8th octave. You can then use that to go ahead and take basic intervals, a major scale interval being whole, whole, half, whole, 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 half, the semitone count between there. You can then take those wholes and halves and turn that into 2 steps or 1 step. Guitar players probably know what I'm referring to. You can then take that and apply that interval against this dictionary and then print out whatever tones or whatever scale you like, starting with your root tone. So if I wanted to start with E, I could then take those intervals and apply them against the keys of that dictionary and print out my scale, which was the intention of this. This is, quote, one of those projects that's in process that I just wanted to point out and give you all some ideas on how to make this work. So far, I've shown you examples in Python, very basic utility, rudimentary stuff. That stuff's really cool, but the real fun is in audio programming and multimedia programming languages. There's a bunch of them out there. Excuse me one second. There's a bunch of them out there, and we're going to talk about a few of them this evening, and I'll show you a little bit in a couple of them. First being C-Sound. C-Sound is an XML-looking script. It runs on a ton of platforms, and it has grown up a mass in the past couple of years. It was just like this when I first ran into it a few years ago, and now it has come to the point where there are actual DAWs where you can take these sound objects, load them into a track and a sequencer, and play them over time. So it then becomes a script, and then you can compose entire scores and things based off of your C-Sound instruments and synthesizers that you make. Additionally, there's an incredibly cool app for C-Sound. I think I'm going to mention it again later, but nope, just mention it here. That runs on iOS. It is called Run Loop Sound, and what that will do is take this C-Sound script and turn it into something playable from a MIDI or Bluetooth keyboard. There's iPad and iPhone support for that, and it takes your imagination and literally makes it so you can do it just about anywhere. It's a really cool library. Definitely, I suggest checking it out if you're into audio or music. Impromptu is another really cool library. It has a lot of graphic support. It does modeling, it does visual, it does audio. The only downside is it only runs on Mac. And I just figured to get a really, give it an honorable mention. Super Collider is another really great library that's very expansive. It's another one of those typed languages. It's super expansive. It runs on just about anything. You can build synthesizers with it. You can build audio effects with it. It does visuals. It does MIDI. It's really cool. And one other really fun note, Aphex Twin, I don't know if anyone's an electronic music fan, but Aphex Twin uses it heavily and likes it a whole bunch. And he, in my opinion, writes some really interesting electronic music. Max for Live and Max MSP. Well, Max MSP and Max for Live, I should say. Max MSP was built by Cycling74, which has recently been acquired by Ableton. And this is different in that it is a procedural node-based programming language in that you don't type anything in that text way. You create little nodes and you link them with little virtual cables. And the cable colors represent what they're passing through them. The solid color cables are data and the stripy yellow ones are actually audio. So you can then take that Max MSP product and put it in Max for Live, which is a subset of Max MSP, and additionally has the addition of the Ableton Live object model. So now you can interact directly with Ableton Live through Max. There's a bunch of really great, awesome built-in things that come with Max for Live. When you grab the Ableton Live suite, there's LFOs and all sorts of cool things that don't come natively in Ableton, but definitely are cool additions. And on top of that, you can then take them, the source code is as open as easy as double-clicking it to open, and they're editable and hackable and customizable and all sorts of stuff like that. There's tons and tons of people who make patches that you can download. There are people who sell patches. It's a really cool library. The only problem with Max for Live is it's around $400 a seat, or the Ableton suite is like $700. Enter Pure Data. Pure Data is a super fun sub kind of thing of that. It's a open source project, runs on all sorts of platforms, has cool graphic support, does MIDI, does audio, does video, has this thing called Gem, which does graphics and audio visuals for you. You'll see a little of that later. So that's a quick rundown of some audio programming languages. There's a couple more out there, actually there's a bunch more out there, but those are some of the more popular ones, the ones I've had personal experience with or worked over or been enticed or amused by. So let's talk a little bit about creation. We did, utility, now some creation. This is a very simple Pure Data synth patch. This one isn't hooked up, but I do have one next that I will show you that is hooked up. And just a quick rundown of what it's doing is the note in takes in a MIDI note from a keyboard or however else you generate your MIDI. It then takes it, unpacks it, repacks it. I don't remember why it does that. And then that phaser there with the tilde at the end is actually an audio object. So before that point, the cable is a little skinnier, and that's actually passing MIDI data through. Once it gets to that phaser with the tilde, that's actually an audio object. So after that point, the cable gets a little thicker, and then you see it goes through a multiplication object, which is then used to divide it against, stand by, I'm sorry. Sorry, that's the frequency, yes. And then the next multiplication that comes through, I'm sorry, no, stand corrected, that's the velocity. The next one that comes through is the volume, and that slider there just moves back and forth and passes a number value that is then put into the right input of that node and then controls the multiplication value of the audio signal going through, hence cutting it down or bringing it to unity gain, and then it goes out through the DAC or the digital audio control. Now this is the patch I do have hooked up. This is one I grabbed off of GitHub. That's the other cool thing about Pure Data, is it's open source and it's a tag on GitHub, so there are copious amounts of projects you can find if you want inspiration or you just want to steal something like I did in this case. So, MacBook do things. And this guy here, as you can see, it's not short in features, it's just in what you want to do with it. There are tons and tons of little nuances going on here, but the quick overall is, on the top left, that's where that note is coming in again, and it does the pack thing. And now it's passing it between some SAW, those are super SAW audio nodes that are being controlled by the stuff on the other side, and what that stuff is doing is that's your ADSR envelopes and stuff like that, and your modulation and filter cutoff. And down here on this side right here is just a really, really simple graph that's just a display of the audio array that's going by. I'm not going to get too much into how each and every component works, because to be completely honest, it would take me a minute to remember, because I haven't had to do this in a while. But the incredible thing about Pure Data is there's tons and tons of support, there's an awesome community, and if you grab any object and control click on it, you then get a help patch. And this help patch is actually a working patch. You can change the values on it, and what it's particularly doing is Moses parts the streams of two numbers. So when you hit a certain point, it starts sending the numbers out the other input for one reason or another to separate things. But absolutely check that out. There is, like I said, tons of help and tons of documentation. And this is just another example of C-Sound. This is a screenshot of the Run Loop Sound program that can be hooked up to any MIDI keyboard through your iOS device or any Bluetooth keyboard through your iOS device and played. In addition to synthesis, there's also samplers, granular synths, sequencers, drum machines, and effects you can build with these audio programming languages. It's really up to your imagination and what examples you can find on the internet. So let's talk a tiny bit about control. One way of controlling music is MIDI, and that's a technical standard. It was devised in the 80s by Roland, and back in the day, it kind of looked something like that. It was a 5-pin connector that sent messages from one piece of gear to another. Those messages had values between 1 and 127 across 16 channels. And the messages usually consisted of a program change, a control, a note, or a system-exclusive message. A program control was intended to tell your synthesizer or sequencer to change a group of patches, go to a new patch or something like that. Control was generally used to change individual parameters. Notes are obviously notes, and system-exclusive messages were things that weren't in those other three categories that your sampler or synthesizer might have wanted to do or have done to it. Commonly now, the system-exclusive messages are kind of just reserved, in the computer world anyway, for changing overall parameters on a controller. So when you would send new patches to your MIDI controller or keyboard, they would be sent through a sysx message. And most controllers now have software that do it for you rather cleanly with a GUI. I like to think of the messages as kind of like a Python list. Generally, you'll have a controller note that is 1 through 127, a velocity or a value, a velocity for a note or a value for control. So they would be known as CCs. So CC 36, you would change the value to 100. And then, like I mentioned, there are 16 channels in which you can pass MIDI messages over that pipe, and basically what that means is you can have different things listening to different channels. I personally use that when I use Ableton Live for production or DJing. I have different tracks listening to different channels. And I'll show you a little bit more about that. And that is just a simple example of a C3 being sent at 127 velocity, which is as hard as you can hit the note, down channel 1. Another way of looking at it or using control is OSC. It's a newer protocol. It doesn't work like that message-based system. It's more modern and it works across networks, and it actually, that's the actual definition, is a protocol for networking sound synthesizers, computers, and other multimedia devices for the purposes such as musical performance or show control. But what it actually looks like is that. It looks like a URL. OSC listens on 9,000 by default at your local host, but the cool thing is you can then use that to pass messages across a network for on top of audio, video, whatever you want. It has tons and tons of support. There's a OSC library in Max, there's an OSC library in Pure Data. A lot of new DAWs are also using OSC now. Ableton not yet, but there are adapters. Osculator. Osculator is a paid app for Mac that takes OSC messages across your network and flips them into actually whatever you want them to be. You can have them run Apple scripts, you can have them flipped into MIDI messages and sent to your DAW, you can have it run shell scripts. It's a pretty interesting protocol. And with that comes iOS support and the networkability and Touch OSC. Now that is, what you're seeing right there is the Ableton Live Touch OSC controller for iPad. It's just a patch, it's completely customizable, you can make your own, completely configurable with whatever messages you want. It makes sliders, it makes buttons, you can have stereo pan knobs, all sorts of fun, interesting stuff, little XY as this thing mentioned there. It then connects to your oscillator or whatever Touch OSC, OSC server you have running and can control it. So Pure Data. Now some actual examples of Pure Data. I have used Pure Data mostly for control, not so much synthesis, although there are a bunch of really cool little things you can do with Pure Data, like there is a node, I can't remember what it's called right now, but it will take an audio signal and do the best it can to turn it into a MIDI node. So then you can then do the best you can with that information to then put it in a synth or some form of sampler instrument and then have it play along with the incoming audio. So it's a quick way of flipping audio to MIDI, which is pretty handy. One of my more recent times doing a live set with Ableton, I used Pure Data to do a little controllerism and use this controller here, which is a super basic controller and only has 12 knobs on it, which didn't exactly do what I wanted it to. So what I then did was created this patch here that what it does is it takes controller message 49, which is the bottom right knob on this, and it controls the global channel of all incoming MIDI. So what's happening in this instance is the controller is sending to Pure Data, and Pure Data is sending to my DAW, Ableton in this case. So when I spin that knob, I use this gem patch to then tell me what channel I'm actually controlling at that moment. Instead of just having the channel numbers, I have a really simple array over here. That down here, this is the text box, and this R is a receive. So what it's doing is it's listening for the global channel information, sending it through the selector. It then picks up what number it wants and then sends the respective text down to my gem window. So as I had Ableton Live up over this, I had this in the bottom corner, and I can control, or I could see what I was controlling without having to flip back and forth to Pure Data. So that was super handy and just another way to use Pure Data in a controllerism type of integration. Additionally, other ways to do that would be to take that similar patch, and what I've done in the past when I've been doing production, actual production work. This is a really cool keyboard I got a billion years ago at Samish in Times Square. And that knob on the left next to digital display actually controls the channel it's sending the MIDI data on, which is kind of unique. Most have buttons, sometimes it's buried in a menu. I enjoy, or I like this controller for that reason, because I can choose on the fly and visually see what I'm doing without the need for the gem patch. But what that then causes the problem is all of the controls on my controller now change to that channel, which gets to be a pain in the butt sometimes when you want that far right fader to be like your master volume, because you never want to blow people's eardrums off and you never want to have to switch back to channel 1 to drop your master volume. So I created a similar patch that would single out one controller message. I think that one was 59, and it excluded it from the global channel changer and just kept it locked to 1. So Ableton knew to listen on channel 1, 449, and that was always going to be my master volume. So it works in both ways. You can control things globally or relinquish other things control. You can initially use it for inter-application routing, inter-device routing. Pure data and its MIDI control is just pretty awesome. So that's computer stuff. Now let's make it a little smaller, a little geeky audio. There's a bunch of unpopular microcontrollers out there, and as you probably saw earlier, there were a couple of audio libraries that worked as source or with Raspberry Pis. So an Arduino is one. It's a little more useful for being a synth or being a MIDI controller interface. The GPIO pins on the left are great to hook up to arcade buttons and joysticks and little knobs and potentiometers. And then you can then use your Arduino. There's plenty of patches, like Raspberry Pis and Pure Data. There's plenty of information on GitHub about this. You can go ahead and find pre-done scripts that will then take voltage changes and flip them into MIDI messages for you, and you can use that USB port to plug into your computer. Additionally, you've got the Raspberry Pi, which, who doesn't love that? It's a computer the size of a credit card, and as you all probably know, it runs Linux. So a fair amount of the packages that exist for Linux for the audio world work on the Raspberry Pi, excuse me. More specifically, C-Sound and Pure Data, which we'll get to that one in a minute. And additionally, another honorable mention is the Teensy board. It's a cool little controller. It is not quite as powerful as the Arduino or the Raspberry Pi, but it is designed to be a human interface controller. So you can use that as another way to create MIDI controllers, use it to control lights and things like that, and then use that to wire into a Raspberry Pi like it's a MIDI controller. So you have the complete customizability of whatever you'd like to make on that little board. It requires a little more DIY with some soldering, but I imagine it's not too hard for most folk. So here's one example. I'm not going to attempt to say Toby Hendricks' stage name, but what this cat did, I was really impressed by, and I figure pass it on to you guys. He did what I had mentioned with the Teensy and the Raspberry Pi. He has, all right, so right there, he has a Raspberry Pi. And up here, it's kind of hard to see, he has a Teensy board and a couple LEDs, and what he's made is this looping step sequencer synthesizer, which is really cool, and I think he said it was under $150, all the parts. So it really kind of means your imagination is your only limit in this. I was inspired to start collecting parts because of this cat. I have an APC40, which is an Ableton-specific controller that has a similar grid and faders and all that stuff. And there's a script on GitHub, again, that has figured out how the hardware-software handshake works between the APC40 and has replicated it for a Raspberry Pi. So now I can basically, instead of doing my own DIY version of this, plug a Raspberry Pi into my APC40 and make my own custom step sequencer synth. With my intention of putting a 7-inch touch display, compliments of my fiance, so I can control Raspberry Pi, the Raspberry Pi's Pure Data on the fly. That graphical procedural-based programming language lends itself very well to doing things with touch screens because you can make big obvious buttons and just push them from your touch screen. Another interesting thing to note about Raspberry Pis and syncing, Ableton in, I believe, their last revision of 9, definitely in 10, has something called LiveLink now. And it is a network protocol for syncing transports, tempo across a network. So multiple, no, Kevin, I'm not really reading them. I'm sorry, buddy. Sorry, the internet checking in. So what that then does is takes Ableton linked enabled applications and makes their transports sync over an internet connection, or over a local internet connection, excuse me. So there's iOS apps that do that, and now there's support for pure data for that. So basically what that means is you can then take your Raspberry Pi Pure Data synth and sync it over a network to your friend's Ableton Live installation or your friend's iPad app that works on Link. It takes all of the things that made electronic music difficult with a partner and just removes the barrier to entry. Definitely look into LiveLink. It's not just for Ableton Live. They created it as an open source protocol. You can actually look at the source code on GitHub, and a lot of places are implementing it. You can use it for iPad to iPad, iPad to Android. There's on the Ableton page, they have a link page and they have listings of all the apps and libraries that support that stuff. So here are some random links. You don't have to write them down. I just want to mention them. I will put them on the GitHub, the Meetup page, or I will also put my email up there. If you email me, I will send them to you. So MIDI Monitor is a great application for the Mac. It's just a way to watch MIDI messages go across your system. I use it for debugging all the time. Super, super handy, especially when working with pure data and wondering what's getting dumped out of your scripts. That one underneath is a great article about waveforms and sound and just how to read them. I borrowed some of the screenshots. The Pure Data manual is awesome. Mentioned for audiocheck.net, great place to get sample files, sine waves, silence, white noise, great for testing. Reaper is a really awesome DAW. It's inexpensive as DAWs go, and the awesome thing about it is it's scriptable in Python and JavaScript too. So if you have things that you do that are repetitive in the production world, like putting the head or tail on your podcast or running it through a compressor or something like that, you can set up these awesome little scripts in this DAW and it'll do it for you. Additionally, you can actually do a lot of those things in SOX too, but it's obviously less graphical and more programming. Below it is the Intro to Synthesis. It's a really cool VHS rip from the 80s or 90s that is now on YouTube in a really, really awesome way to learn about basic synthesis. There's the links for the gentleman's Raspberry Pi thing, all the videos, and the synth that you saw earlier. Thank you very much for coming. If you have any questions, feel free to take down my information. I love collaborating, I love chatting, I want to hear what you people are doing. Please keep in touch. Thank you all.